Hello, welcome back everybody to Math 1351, more on math. Today we're going to talk about Chapter 9, Section 4. Section 4 deals with counting techniques. Our objectives for this section are going to discuss the fundamental counting principle, permutations, permutations of like objects, combination, use of counting techniques in probability problems. Now, basically, why do we need to know the counting techniques? Because it won't always be so simple like we had probabilities. You need to have part over total. Trying to determine the total number of ways an object can be done, or even the partial way, it may take a lot of tries. So this way we'll learn shortcuts to determine if we do a specific object, a specific event, then we can determine how many times that event can occur. So, counting techniques are used to find a number of elements in an event and the same sample space. So if we're the sample space of how many ways can an object occur, we know that flipping a coin, it's heads and tails. One die, it's 1 through 6. Two dies, it's 2 through 12. But what happens when we go from there? What if we have groups of people? What if we have a group of 25 people and we have to pick a president, vice president, and treasurer? Now, we can't do that with what we've done so far. Now we have to learn new ways of doing it. So let's begin. In Chapter 2, we discussed the fundamental counting principles. What that says is, if an event M can occur in M ways, and after M occurs, then event N can occur in N ways. Then event M followed by event N can occur in M times N ways. Okay. If one event happens, and it can happen a certain number of ways, let's say 5 ways, and then after that finishes, there's another event that can happen. It can occur 4 ways. So to figure out the total number of ways these two events can happen is you multiply them. 5 times 4, it can happen 20 different ways. So that's the basic outline of what's talking about here. Now we're going to discuss something called factorials. So let's look at, in other words, let's see this. If we have two objects, A and B, how many ways can you arrange those? How many different ways can you arrange them? We have A and B, and we have B and A. So equals 2 ways. Let's get bigger. What if we have 3 objects? A, B, and C. Same question. How many ways can we do that? So let's look at this one graphically. Event A is the first one, or we could do event B, or we could do event C. Remember, you have to use all 3 of these letters. So if event A happens, what do we have left? We have B and C. So after A, you can have either B or C. If you did B first, then you can have either A or C. If you did C first, then you can have either A or B. Now, you have A, B, then after B, you have to use C. If it's A, C, then you have to use B. If it's BA, then C has to come last. If it's BC, then when we need an A. CA, we're missing a B. CB, we're missing A. This happens 6 times, 6 ways. And it gets more complex from there. If we had 4 objects, we'd do it 24 ways. Alright, so This is where we introduce the concepts of factorial. Whenever you see a number, let's say like 3 factorial, what that means is whatever number you have in front of it, multiply that number all the way down to 1. So we have 3 objects, 6 different ways. If we had 2 objects, 2 times 1. If we had 5 objects, 5 factorial is 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is 1. There's 120 different ways you could arrange them. So factorial is multiply all numbers from whatever number you have, n, down to 1. We have to stop at 1 because if we went to 0, then it'd be 0 since we're multiplying. All right? Because we're also going to need this symbol in the next 2 formulas we're going to talk about. Okay, the next thing we're going to talk about are called permutations and combinations. Permutation is per each change. Combination is just combine. Alright, so now what's the difference? In permutation, it says per change, order is important because we're looking at each change. So AB is not the same thing as BA. When you combine items, when you combine, order is not important. AB is not equal. So AB is the same thing as BA is. As long as I have those 2 letters, I'm happy. All right, let's look at an example here. Let's pretend. We have 4 objects. Let's call them A, B, C, and D. We want them in groups of 2. How many can you do this? Remember, we have A, B, C, D. We can have AB, AC, AD, BA, BC, BD, CA, CB, CD. I can't have AA because I only have one A to choose from. I can't have a BB, I only have one B to choose from. So each letter has to be different. So the last column is I can have DA, DB, DC. Let me copy those over here again, and I'm going to show you the difference between the 2. AB, AC, AD, BA, BC, BD, CA, CB, CD, DA, DB, DC. All right, let's look at two different ways. In permutations, order was important. So AB and BA are totally different. CA and AC are different. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 different ways. However, in combinations, AB and BA are the same thing. So I can't repeat them both, so I have AB, BA, both the same thing there. AC, I don't need CA. AD, I don't need DA. BC, same thing as BD, same thing as DB. 1, 2, 3, 4. I only have 6 ways. Now, the difference between the two. Let's say combinations is an example of that is qualifications for the Olympics. As long as you finish within the first 2, you get to go. So you have 4 racers. Whoever finishes in the first 2 goes. So it's runner A, runner B. So I don't care who finishes, they both go. So whether A finishes first or A finishes second, they get to go to the Olympics. Now, permutation is at the Olympics. Olympics. Winner gets the gold. Second gets the silver. Third gets nothing. So yes, now it does matter on how you finish. If A finishes first, gets the gold. But if A finishes second, gets the silver. Those are the differences. Permutation, it matters how you finish. Combination, as long as you finish. Alright, so let's look at the two. What a permutation. Permutation is an arrangement of objects in a specific order with no repetition. Again, permutation is an arrangement of objects in a specific order with no repetition. So what we saw earlier, we had 6 objects. There's 6 times 5 times 4 times 3 times 2 times 1. No, we said no. So 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360. 360 times 2 is 720. 720 times 1 is 720. So if you have 6 objects, you can arrange them in 720 different ways. If you had 3 objects, you put them in 6 different ways. So our formula, the permutation formula, NPR. Numerators n factorial, the denominators n minus r factorial. N is the total number of objects you have. R is the size of the groups desired. Let me explain what that means. Okay, so that's N and R. Oh yeah, also R has to be between 0 and N. It's always the bigger number and the smaller number. So R always has to be less than or equal to N, but you can't have negative numbers. Because we're talking about objects. You cannot have a negative object. So example. Three objects can be ordered in how many different ways? Different capital word. So N is the total number of objects. R is how many elements in each group. Well, since there doesn't say any specifications, it has to be 3. So our formula NPR becomes 3P3 remember, it's n factorial over n minus r factorial. So n is 3, 3 factorial, 3 minus 3 factorial, 3 minus 3 is 0, 0 factorial is 1. So it's 3 times 2 times 1 over 1. You can put them in 6 different ways. Here's another example. You have nine actors. All of them act. But the restriction, no actor can have multiple roles. That's A. B. Not something like that. A. B. Choose 3 letters from the alphabet. And C. Choose 2 numbers from 1 through 10. Let's look at this. Okay, so A. N, we have 9 actors. All actors, no actors can repeat multiple roles, so we have to use all 9 people. So since they're all different roles, N is 9, and R is 9, so it's 9P9. 9 minus 9. So 9 minus 9 is 0 factorial, so that becomes 1. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Get your calculator out. You'll get 362,880 different ways. You could arrange 9 actors to do the roles. Okay, N. You have choose 3 letters from the alphabet. The alphabet has 26 letters. You have to choose 3. Remember, R has to be between 0 and N. So the bigger number is always N. So it's 26 permutation 3. 26 factorial. 26 minus 3 factorial. 26 minus 3 is 23. Now, the beautiful thing is, in factorials and combinations, you can never have denominators. They always cancel. So, if we think about this one, 26, 25, 24, 23 down to 1 cancels with that one. This is 23 down to 1, that's 23. So all we're left with is 26, 25, 24. If we multiply those, we'll get 15,600. You have 10 numbers, and you want them in groups of 2. So it's 10p2, 10 minus 2, 10 times 9, 8 factorial cancels, so 8 down to 1 cancels. So all left is 10 times 9, which is 90. So that's the way you use permutations, and it gets much easier as we start going along. Okay, these are all of unlike objects. Because, I mean, you have 9 actors, not all the same person. You have, each letter is different. You have different numbers. So now what happens if we have permutation of like objects? So we have 2 different objects, R1 and R2. This could be cereal boxes. This one would be milk cartons. N is the number of R1 plus the number of R2. Remember last semester we talked about cardinality. The cardinality of R1 plus the cardinality of R2. So here, the permutation is n factorial, R1 factorial, R2 factorial. So if we had more, we'd R3, R4, R5. But add the number of those, that equals n, and divided by each one separately. If there are n objects, of which R1 are like, R2 are like, and so on and so forth to Rn are alike. Then the number of different arrangements of all objects when all alike objects are indistinguishable. You can't tell them apart. This is all equal to n factorial. Remember, n is the summation of all the cardinalities of each group. The number, cardinality is the number of each group, divided by the product of each cardinality. So, again, it's if there are n objects of which R1 are alike, R2 are alike, Rn are alike, the number of different arrangements of all objects, when all alike objects are, you can't tell them apart, so they belong in each group, it's equal to n is the total number of all the objects you have, divided by each group separately. So let's look at the example here. You have the word bubble, and you have the word statistics. How many arrangements are possible? So, let's look at the first word, bubble. So we have the letter B. It occurs 3 times. The letter U occurs once. Letter L occurs once. And letter E occurs once. So if you add them up, 3 plus 1 plus 1 plus 1, that equals 6. That's my n. So n equals 6. We have 6 letters in the word bubble. So the number of possible ways are 1 factorial, 1, 2, 3, 4. You have R1, R2, R3, R4. So it's 6 factorial divided by 3 factorial times 1 factorial times 1 factorial times 1 factorial. 1 factorial is simply 1, so I don't need those. 6 times 5 times 4 times 3 times 2 times 1. 3 times 2 times 1. Remember, you can never have a denominator, so those cancel. 6 times 5 times 4 is 120 different ways. Let's look at the next one. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n equals 10. S occurs 3 times. T occurs 3 times. I occurs twice. A occurs once, and C occurs once. So the number of arrangements possible are 1, are 2, 1, 2, 3, 4, 5, are 3, are 4, are 5, which is 10 factorial, that's n, 3 factorial, 3 factorial, 2 factorial, 1 factorial, 1 factorial. Again, we don't need the ones. Times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's the top. Now 3 factorial. 3, 2, 1. Next one. 3, 2, 1, and the 2. So 3, 2, 1 can cancel. 3 times 2 is 6. 2 goes into 4 twice. Times 8 times 7 times 5 times 2. Multiply all those together, we get 50,400. So I have to be very careful about how you arrange those, because, yeah, I mean, if you get lost canceling things out, you'll cancel too many. So those are permutations, each different ways they could be arranged. Now let's talk about combinations. A combination is an arrangement where order makes no difference. It's not important. Remember, it's just like I said earlier, the combinations are the qualifications. The top 3 finishers go, everybody else is out. The permutations is the actual competition. If you would finish first, you get first. If you get finished second, you get second, so on and so forth. So the difference of the two are let's look at the letters A, B, C. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. These are all different in permutations. In combinations, these are all the same thing. So again, combination doesn't matter the order. You still have 3 letters, A, B, C. That's all it takes. Permutation, each order is important. So to find a combination, divide the permutation by the number of ways n objects can be arranged that gives us a combination. So again, divide the permutation. Remember, so we have NPR. Divide that by the number of ways n objects can be arranged. So it's n factorial. So permutation is n minus r factorial all over n factorial. Take the top fraction, leave it alone, times the flip of the bottom. So we get the combination formula is the same as the permutation, except we divide the bottom by that. Okay, and no, it's not. You can't just cancel the n factorials and get 1 over n minus r. That doesn't work that way. If you do that, then we get a fraction. So do not cancel n factorials. They're actual numbers. They tell us the number of ways objects are possible. Get another piece of paper here. So for combinations, remember, r has to be between 0 and n. And our formula is okay. Over here, originally I said the way we have n objects taken care of. But that is the problem. It's not the total number of objects, it's the ones we want specifically looked at. Those are the ones we can combine. So here, n, I'm looking at n. This r is supposed to be that n. So how many ways can we readjust those smaller numbers? So, for example, three cans from a shelf of 42 cans. Can be arranged in how many combinations? So n is always the bigger number, r is the smaller. Remember, our formula is NCR, n factorial, r factorial, n minus r factorial. So 42 C3. 42 factorial, 3 factorial, 42 minus 3. (42 minus 3 is 39). So 42 times 41 times 40 times 39 down to 1 cancels with 39 factorial. So it's 42 times 41 times 40, 3 times 2 times 1. 3 goes into 42 14 times. 2 goes into 14 7 times. So the number of combinations possible, 7 times 41 is 287. 287 times 4. 34. 11,480. So you could arrange 3 cans. If you have 42 to choose from, you could arrange them 11,480 different ways. All right. Another example. You have a room of 25 people. Have each person shake hands with each other only once. So no, you can't shake the same person's hand twice. What is n? N is your number 25. And when you shake hands with people, it's 2 people each time. You and the person you shake hands with. So 25C2. Remember, it doesn't matter how you shake hands with it, which order, because order is not important here, because it's all randomized. So we have 25 factorial, 2 factorial, 25 minus 2 factorial, (25 factorial, 2 factorial). 25 minus 2 is 23 factorial. So 23 down to 1's gone, so we have 25 times 24. 23 down to 1's gone because of that. Half of 24 is 12. So 25 times 12 is 300. 25 times 10 is 250. 2 times 25 is 50. 250 plus 50 is 300. All right. Counting techniques in probability. Let's look at the lottery. To win the lottery, you have to pick 6 numbers from 1 to 55. So it's 55. And is order important how you pick them? Nope. So it's combination. So we have 55 factorial, 6 factorial, 55 minus 6 factorial. (55 minus 6 is 49. So it means 49 down to 1's gone. So we have on top 55, 54, 53, 52, 51, 50. Plus 49 down to 1's gone. 6, 5, 4, 3, 2, 1. Okay, 6. Let's see here. 2 goes into 50 25 times. 5 goes into 25 5. 3 goes into 51 17 times. 4 goes into 13 times. 6 goes into 54 9 times. 55 times 9 times 53 times 13 times 7 times 5. Equals 28,989,675. Now, what does that mean? It's 1 in 28,989,674. Remember, it's 675. So your probability of winning is 1 over... That's the probability of winning. Not likely, huh? Let's have another example. Okie doke. You have a room full of 22 students. 12 are girls, 10 are boys. Create a committee with 3 girls and 2 boys. What is the probability of A happening? Create a committee with no boys, which means 5 girls. What is the probability of C occurring? Let's look at this. A. We need 3 girls, 2 boys. And N is 22. Doesn't matter how you choose them. Order is not important. They're each going to be inside the committee. So, what we have to do here, here's combination of girls times the combination of boys. We have 22C3 times 22C2. No, 12 and 10, I'm sorry. They're subgroups. This is a committee just of girls. There's 12 girls, you want 3. 10 boys, you want 2. Sorry. So 12 factorial, 3 factorial, 12 minus 3 factorial, times 10 factorial, 2 factorial, 10 minus 2 factorial. 12 minus 3 is 9, so 9 factorial is gone, so it's 12, 11, 10. 10 minus 2 is 8. So 8. So all we have here is 10 times 9. 8 to 1's gone. Three times 2 is 6. That goes into 12 twice. 2 goes into 10 5 times. 2 times 11 times 10 times 5 times 9. 99, 100, 10, 99 times 10 times 10 is 9,000. So it could happen 9,900 times. So the probability is 1 over, no, is, since we're dealing with two groups, I'm sorry, it's 22 combination 5 over the girls and the boys, which is 12C3, 10C2. Oh, that's backwards. The bigger number is always going to be on the bottom. 22C5, that's the total possibility, and now each individual, so it's 12C3 times 10C2. We know these two possibilities is 9900. Now we just gotta find this one, 22C5. Minus 5. 22 minus 5 is 17. So 17 times a 1 is gone, so it's 22, 21, 20, 19, 18. 5 times 4 times 3 times 1. 5 times 4 is 20. 3 goes into 21 7 times. 2 goes into 22 11 times. 11 times 7 times 19. $26,334. So that equals, so you have a 37.6% chance of that happening. I'm sorry about this. The bigger number always goes on the bottom for probabilities. Okay, now we look at committee of all girls. So committee of 5 girls. So here's the girls, here's the boys. There were 12 girls, and we want 5. 10 boys, we don't want any of them. So we have 12 factorial, 5 factorial, 12 minus 5 factorial, 10 factorial, 0 factorial, 10 minus 0. Remember, 0 factorial equals 1. So it's 10 factorial over 10 factorial, that equals 1. So we have 12 factorial. 12 minus 5 is 17. It's 7, not 17. So 7 down to 1's gone, so we have 12, 11, 10, 9, 8. 5, 4, 3, 2, 1. 2 times 5 is 10. 4 times 3 is 12. So we have 11 times 9 times 8. 11 times 72. 11 times 72, so 11. 72 plus 720. 792. All right, so that's the probability of getting all girls. Now that's the combinations of choosing 5 girls from the 12. All right, this was 1. So we have 792 divided by 26,334. That equals 0.03, or a 3% chance of getting all 5 being girls. Sixth question, true or false test. Oh, it's an Amber Alert. Okay, what's the probability of guessing? Correctly. So, to get it correct, we know that it's 1 out of 2 possibilities, which is 50% chance of getting them all right, or each question right. Now, if we did that, if we did 6 over 6, it wouldn't work. So that's not going to work, so we'll look at it this way. We have 6 questions. All of them are 1/2 of getting them correct. Yeah, 50% chance, so that's 1/2 to the 6th power. Which is 1 over 2 to the 6th. So your probability of guessing them all right, so it's 2, 4, 8, 16, 32, 64. 1 over 64. All right. All right. Good luck, everybody.